Now that we've learned how to make atomic diagrams and seen what valence electrons are, we can look at how elements are bonded together to make new chemicals called compounds. So bonding only occurs through electrons, and importantly, it only happens between the valence electrons. So valence electrons are very, very important. We need to know how many there are. They tell us how things will bond together. Here is an example of Einsteinium. Look at how many electrons there are. There's 99 electrons, and yet the only two that matter are the outside ones, which are our valence electrons. That's because bonding can't occur closer into the element. It's only on the surface that these things bond. So valence electrons are super important. You need to know how to find the valence electrons. That will tell us how bonding occurs. Another important factor is to recall that the maximum number of valence electrons is 8. So recall, group 1A has 1 valence electron, group 2A has 2 valence electrons. All of the group B, which includes all those lower ones in that lower part of the periodic table, all of those have 2 valence electrons. Group 3A has 3 valence electrons. Group 4A has 4 valence electrons. Group 5A has 5 valence electrons. Group 6A has 6 valence electrons. Group 7A has 7 valence electrons. And, of course, Group 8A has 8 valence electrons. Now, what's exciting is for the valence electrons, they always want to try to get to 8 or 0. We're going to talk about why we can get to 0 sometimes. But they always want to get to that magic number of 8. That's kind of what we're looking for. And so valence electrons for noble gas is already 8. So those ones are already satisfied. And that explains why they don't like to bond, because they already have their 8 valence electrons. But let's see what happens for all of the other ones that need to try to get to 8 valence electrons. We're going to use something called the Lewis electron dot symbol. And we're going to do that first for our elements, just so we can see how many valence electrons each one has. And then we're going to talk about how we can get them to 8 electrons through chemical bonding. So let's start with our basics for our elements. To do an electron dot symbol, we're going to do a really simplistic idea first. We're going to talk about a basic symbol, something that isn't a real element, but just to give you a model of how to do it. So, Lewis dot symbols, each dot represents a valence electron. Only the valence electrons. We do not count the inner electrons at all. And when we're drawing these dot symbols, the first thing is we write out the symbol for the element. That's so we know which one we're talking about. And then we're going to put this with 4 different sides, kind of like a square. And those are the only places that you're allowed to place electrons, are on those 4 sides. We can put 2 on each side of the element. But we're going to always put those electrons in place one at a time. So if I have just 1, of course I put in 1. If I have 2, I have to put them on 2 different sides. The electrons don't want to pair up. So I think of this as going on a trip with your family, let's say. So you've got all your brothers and sisters and you're going somewhere. You go to this hotel and it happens to have 4 beds and there's 8 of you. You're going to have each have 2 of you in each bed. But if there's only 2 people, you'll each take your own bed. You won't slip together. Then you go to the 3rd bed when there's a 3rd person, and the 4th one when there's a 4th person. And when the 5th brother or sister joins you, then one of you has to pair up. We call that a lone pair once they start pairing up. And then we go to the next one and we continue around again. So you add 1 electron at a time, and then you start pairing them when you have to. And then there's a few details about how we draw them in. We never draw them in the corners because it has to be on one of the 4 sides. So make sure that they don't go into the corners. And then the next thing is that they always stay close to the atom, so they're not sticking out in any way. If they are sticking out, that means that they're bonded to something else, and that's coming from another source. So we want to actually make the electrons be attached to this atom, not bonding from something else. So we're going to draw them nice and close. So we'll draw them in lines, not like this, and of course not sticking out like this. So those would be incorrect structures. And that's kind of the basics for Lewis dot symbols, and we'll go ahead and do some examples on the next set. So just a real quick reminder of how many valence electrons we have. We have 1 for group 1A, 2 for 2A. All of this section is 2 valence electrons. Then 3 for 3A, 4 for 4A, 5 for 5A, 6 for 6A, 7 for 7A, and 8 for 8A. Remember, helium only has 2 valence electrons because it only has 2 electrons. Let's do an example for oxygen. Just draw it out really quickly. We draw the O in the middle. We draw 1, 2, 3, 4, 5, and 6. If we look at oxygen, it has 2 lone pairs plus 2 electrons that are free to bond. So let's focus on just the third period. We'll start with sodium. Sodium is group 1A, so it has just 1 dot. That dot can go on any one of the 4 sides. So it could be here, or here, or here, or here. Top, bottom, right, or left, doesn't matter. That's it. Then we look at magnesium. We can draw it in several different ways. We can put top and bottom, left and right, top and left, top and right, bottom and left, bottom and right. So there's a lot of choices. It doesn't matter which one you choose as long as you don't put the electrons together. We don't have anything in the third period with the B series, but we do know that all the lower ones do have the B group. The B group ones all have 2 valence electrons, so they'll look exactly like magnesium. There'll be no difference. We go to group 3A. And then group 3A, we have 3 dots. So again, we're going to put 3 dots, and they can go in a variety of different positions. So let's draw those out. And again, you can choose whichever one of those you want to. It doesn't matter top, right, left, bottom, as long as they're not paired up. Okay, let's do silicon. Silicon is in group 4A. It has 4 dots, and that's 1 on each side. There is no choice. It's all going to look the same. Now let's go to group 5A, which has phosphorus. We're going to see 1, 2, 3, 4, 5 dots, and one of them is going to be paired. It doesn't matter top, right, left, or bottom, but all the other positions will have 1 pair electron. So of course we can have these other drawings. We do sulfur at 6A. It's going to have 1, 2, 3, 4, 5, 6. 2 of them are paired up. Those are our lone pairs, and 2 of them are single, very much like we saw for oxygen. And then we have these other versions. Again, it doesn't matter which ones are paired and which ones are unpaired, as long as there are 2 paired, 2 unpaired sets. And then we go to chlorine. It is group 7A, so there's 7 dots, 1, 2, 3, 4, 5, 6, 7. And again, we have different versions where we have the single electron on either the top, the bottom, the left, or the right. It doesn't matter. And then we have argon, which is group 8A, which has 8 dots. So all of the sides are filled, and again, we don't have a choice. There's only one way to write the noble gases. Next, we're going to look at how they bond. This will depend on how many valence electrons there are, how many are paired and how many are unpaired, and whether something is a metal or a non-metal. Atoms always try to become as stable as they can. The most stable position they can have is to have 8 electrons in their valence shell, but they can't get there on their own. So they start bonding to other atoms. There are 2 ways to get to the correct number of electrons. One way is to share electrons with another atom. If they share the electrons, they both get to count those electrons as if they were theirs. Sort of like going to the bank and you put in $10 and your husband or wife puts in $10, and then you put it all together and you say, well, we have $20. And for our atoms, what they think is they each put in 1 electron, so they each think they have 2 now. That would be like us thinking that we each have $20 in the bank. Not good for banking, but it works out for these atoms. So as long as they think that they have the 2 electrons, it counts as 2 for each of those atoms that are bonded. So every time we make a bond, they're going to count for 2 electrons. The second way to get to 8 electrons is to gain or lose electrons. If we gain an electron, we get a negative charge. If we lose an electron, remember electrons are negatively charged, if we lose an electron, we get a positive charge. How do you know if you're going to gain or lose electrons? Well, it depends upon how many electrons you have. If you only have 1 electron, it's easier to lose 1 electron than to add 7. So we're going to look at how many there are, and that'll be on our next section.